In this video, we'll review some basic calculations on how to prepare pH buffers. If you could remember, pH buffers are solutions which resist drastic changes to pH. If you want to review how that works, please review Le Chatelier's principle. Let's consider this equilibrium reaction. If we have an acid A interacting with water to form the base B, its conjugate, and hydronium ion, we know that the acid dissociation constant is the equilibrium constant. So the Ka is equal to the concentration of base times hydronium ion divided by concentration of acid. Now, what if I want to isolate the hydronium ion on its own side? So if I wanted to have hydronium ion alone, the following transformation should make sense. That should be Ka times concentration of acid over concentration of base. I will now apply the negative logarithm to both sides. So the negative logarithm of hydronium ion concentration, negative logarithm of Ka times concentration of acid over concentration of base. The negative logarithm of the hydronium ion concentration is pH. By rules of logarithms, we can separate Ka and concentration of A over concentration of B by the following. This is negative log of Ka plus negative log of concentration of A over concentration of B, which means to say that pH is equal to pKa minus log concentration of acid over concentration of base, which is also equal to, due to the properties of logarithms, pKa plus log base over acid. This final form is called the Henderson-Hasselbalch equation. So if you have a buffer and you know the equilibrium concentrations of the base and the acid, or more specifically the concentration of the acid and its conjugate base, then you could easily calculate for the pH. However, even if the Ka describes the equilibrium concentrations, we can use the Henderson-Hasselbalch equation to calculate for the desired molarities if we wanted to create our own pH buffer. So I will show you how that will work. Suppose that we are tasked to prepare 100 milliliters of 0.1 molar pH 7 phosphate buffer. Phosphate exists in four forms. Of course, there's phosphoric acid, H3PO4, and then H2PO4 minus, HPO4 2 minus, and PO4 3 minus. In the Henderson-Hasselbalch equation, we need pKa. This is also the reason why I did not include phosphate anymore, because phosphate is not an acid. The first thing that I will do is to calculate for the pKa. Negative log of 7.1 times 10 to the negative 3 is 2.15. Negative log of 6.3 times 10 to the minus 8 is 7.20. And negative log of 4.2 times 10 to the negative 13 is 12.38. If we are tasked to create a buffer solution of a particular pH, we need to find a pKa value that is 1 unit more or less away from this pH value. If you could see, the pKa of H2PO4 minus is precisely that. It's very close to pH 7. So our acid must be H2PO4 minus, and our base is its conjugate. It's HPO4 2 minus. When we say 0.1 molar, the concentration of the acid and the concentration of the base should be equal to 0.1 molar. So, even if the Henderson-Hasselbalch equation describes equilibrium concentration, we can use it to describe initial concentration, and we can just correct it later. I know my desired pH, it's pH 7. I know my pKa, it's 7.2. What I need is my ratio for base over acid. So if I subtract both sides by 7.2, 7 minus 7.2, and then I take the anti-logarithm, that's 10 raised to 7 minus 7.2, base over acid should be equal to 0.6309573. Again, because I know that A plus B is 0.1 molar, this is just the same as B over 0.1 minus B is equal to 0.6309573, meaning that if I resolve this equation, B should be 0.038863 molar. Following the same logic, A plus B should be 0.1. A is then 0.1 minus this value, 0.0386863. It should be 0.0613137 molar. Now that I have the molar concentrations of the acid and the conjugate base, I need to find the corresponding molar masses of the salts. So I have here the molar masses of the potassium salts, pure analytical grade reagents, which I can use for my buffer. For the acid, it's 136.09. For the base, it's 174.18. So the grams of acid should be 0.0613137 molars. It's 100 ml, so it's 0.1 liter. This becomes moles of acid, and 1 mole of that is 136.09 grams. This is 0.8344 grams. The grams of base is 0.0386863 multiplied by 0.1 liter. Convert the moles of base to the molar mass of the salt, 174.18 grams. This should be equal to 0.0386863 times 0.1 times 174.18, 0.6738 grams. If you don't quite see the conversions that I did, let's take a closer look at the base. This is 0.0386863 moles of HPO4 2 minus per liter times 0.1 liter, the final volume, cancel out. We're left with moles. There's 1 mole of HPO4 2 minus for 1 mole of K2HPO4. So we're left with moles of K2HPO4, and I provided the molar mass, which is 174.18 grams per 1 mole of K2HPO4. So hopefully that is clear if you didn't get it that time around. Now we have the grams of acid in terms of potassium dihydrogen phosphate and the grams of base in terms of dipotassium hydrogen phosphate. We also call this the monobasic phosphate and this as the dibasic. We can then propose a way to prepare the solution. So first and foremost, weigh 0.8344 grams monobasic phosphate, potassium phosphate, and 0.6738 grams of dibasic potassium phosphate. Dissolve and dilute to 100 ml. And since there might be some small errors in pH or some small deviations, adjust to pH 7 using drops of 0.1 molar hydrochloric acid or 0.1 molar sodium hydroxide. So using the Henderson-Hasselbalch equation, we could propose for a way to prepare for a buffer solution of a desired concentration and a desired pH.